Okay, so first of all, when we want to use the emulator, it's the easiest way is to go to Google and write emulator 8086. You can go to the emulator and you just go to emulator 8086 and download it on your PC. It's very simple download. You'll find that it's quite a small program. What is it? See here, application, save. It's just 3.1 megabytes. That's it, and then you can install it very easily. It's just a small program for the emulator. I think it's already installed on this computer. Okay, so that's the installation process of the emulator. Now see here, finish, launch. So now the emulator will start working, and it may require registration. If it's not registered, then you need to register it. So now it's working. You can see here that for me it's working fine and everything is well, and it's registered. If you want to find registration, you just go and write here on Google the emulator 8086 key. You just write key and you are going to find a lot of keys. See here, just the first option I took. Here is a user and here is a key, and that's it. Quite simple. I will not upload anything for this emulator. It's already there, and you can start working on it on SULMS. On module 3 I have uploaded here an emulator 8086 video which is explaining how to work with the emulator 8086. Miss Alia will also go through the emulator and explain it for you. I have also uploaded a pre-recorded video for the registers, and of course, like the previous module, all the lectures that we discussed will be uploaded inside the folders. You can see here that inside the folder, each class that I gave to you is uploaded over here. So this is how it is going to be done. So I will start now talking about the programming. The first thing to talk about when we talk about programming in the microcontroller is the addressing modes. The addressing modes, the microprocessor has different addressing modes. You can access the data in many different ways. We need to understand how these addressing modes are working and how we access the memory and retrieve the information from the memory. This is a very important part, because part of understanding how to write a program is how to retrieve the data and how to store the data inside the memory. Remember, we have very limited number of registers. Our registers are mainly AX, BX, DX, and CX. We have the instruction pointer, we have the stack index, source index, destination index, the stack pointer. All of these are registers, but again, they are very limited registers, so it's very important to know how to access the computer memory and in order to deal with these issues. So the machine instruction, as you know by now, that each instruction inside the assembly language is having its own hardware circuit inside the processor. So machine or computer instructions are instructions which, when executed, determine an operation of the CPU, constructed using binary numerical values. These symbols such as add, sub, mul, div, move. Add is for addition, sub for subtraction, mul for multiplication, div for division, move to store data or to move data around inside the CPU. So these are the things that we are talking about inside the emulator. Okay, inside the emulator, sorry, how is this translated inside the emulator? So if I write a very simple program, which is, I will start with origin 100 hexa. Then I will move to AX 345 hexa. This is a move instruction. Move to BX 11 hexa. So if I write H at the end, this means hexa. Then add AX BX. So this is a simple program. Once I run it, I want to show you this over here. Now if you look over here, this is my move AX and these numbers. Now this move instruction is basically B8 inside the processor. This is B8 in hexadecimal, this is B8 in decimal, and this is a symbol for B8. So you can see here, move AX is basically inside the microcontroller is B8. Then 5604, 5604. This is how it is stored inside the processor. So if I want to write a machine code for this microcontroller or microprocessor to do what? To do move AX, then I will write just simply B8. So this is the actual instruction inside the memory. So you can see here, this is our memory. It starts at 700 and the instruction starts at 100, since I said origin 100 hexa. So these instructions, each one of these instructions has its own code, or what we call an op code or operation code. Each operation code, the machine will understand it and it will deal with it inside the processor. So the instruction types, we have mainly three types of instructions. The collection of different instructions that the CPU can execute is referred to as the CPU instructions. These instructions are memory movement. These instructions are the memory movements. Let's double check here very fast. The memory movement instructions are memory instructions and input-output instructions. These move the data, such as the move instruction. Then we have the data processing instructions, such as the add, the subtract, and or. All of these are arithmetic and logical instructions. And finally, the control instructions, program control instructions. Basically, these instructions are for the jump, for the loop, for the bit manipulation, and call and return instructions. These are control program. These instructions, basically they deal with the program counter. These instructions, they deal with the program counter. These are the arithmetic and logical instruction, and these are basically the input-output instructions and move instructions, which we are going to talk about this time. So an instruction format is basically different from processor to processor. You already took an example in the lab in the previous module. An instruction format will consist of the layout of the bits. So for these 16 bits, we can have the first 4 bits for opcodes. If we have 4 bits for opcodes, this will give us 2 to the power 4, which is 16 different operations that can be associated with this instruction format. Then we have 6 bits for operand reference and 6 bits for operand reference. Now this can change. Most basic issues is the instruction length. We can have instruction length of 16 bits, they can be 32 bits or 64 bits, depend on the complexity of the instruction we are working with. So the most basic issue is the instruction length. Longer instruction length permit more opcodes, addressing modes, and addressing ranges. Longer does not imply a significant increase in functionality. لأنه remember, each function that you are going to add inside the processor over here, you need to have the hardware support for it. لما أنا بحكي when I say add معناته لازم يكون عندي I need to have the addition or the circuit that will do addition between two numbers. When I say subtract, I need to have the circuit that will do subtraction between these two numbers. فالموضوع it's not only just add instructions and that's it. لا. Each instruction you need to have the hardware support for it. If you don't have the hardware support for it, you cannot add it. Instruction lengths are equal to the basic memory data transfer size. If the memory is 32-bit words, then the instructions would be 32 bits or 64. عادة we can cascade two memory locations and make them one. So it's either 32, it can be 32 or 64. If it was 16, it can be 16 or 32. Now the affected by and effects. What are the effects that can have on the length of the instruction, which is the memory size. لأنه if you want to address a memory, then you need to have the number of bits over here supporting the size of the memory. How is the memory organized? The bus structure. If you are going to transfer 64 bits on a 32-bit bus, how is it done? How is the CPU complexity and the CPU speed? We have some trade-offs when it comes to these things. The trade-offs between the powerful instruction and saving space. If you have powerful instructions, then you will need to have more space. If you have less powerful instructions, you will have more space. Also, we have another trade-off between the number of opcodes supported and the power of the addressing capability. Now, here I have only 16 instructions because I have 4 bits. Now, if I increase 1 bit over here and have 2 to the power 5, which is 32 instructions supported, then these 6 bits will be 5 bits. So, whatever I gain here, I'm going to lose over here or over here. So, you need to have some trade-off between the addressing capabilities and the number of instructions to be supported. Now, the allocation of bits depends on the addressing modes. يعني ايش allocation of bits? When we come to the instruction format over here, and let's say I have 16 bits my instruction has a length of 16 bits. The trade-off is or the allocation of bits. How do I distribute the bits? Depends on the following: the number of addressing modes. How many addressing modes do I have? The number of operands, because we have instructions of 1 operand. We have instructions with 2 operands. And we have instructions with 3 operands. So over here, if I'm using only 2 operands, then 6 bits, 6 bits. 6 plus 6 is 12. If I have them as 3 operands, then I will have each operand of 4 bits. So the number of operands is important. Register versus memory. Am I going to depend on the registers or going to depend on the memory? How am I going to access the memory? Am I going to access the memory through the registers or what? Depend again on the addressing modes. The number of register sets. The number of register sets. The addressing range and the address granularity. So these, how to access the address, is it easy to access it or not? Basically, these are the factors that affect the bits allocation inside an instruction format. So to get the best solution, usually they do some trade-offs between the allocations. However, in assembly, we have the instruction needs to specify few things, which are the operation code. What instruction, what is the operation that I'm going to execute? يعني if I have an instruction format, it first needs to tell me the opcode. The opcode for addition, for subtraction, multiplication, add, or, subtract, jump, all of these, they have different opcodes. Specifies the operations to be performed. The operation is specified by a binary code known as the operation code, or we call it an opcode. Source operand reference. The operation may involve one or more source operand. Usually you have here operand. Okay, that is the one or more operands. Maybe you have one or two operands. This is operand 1 and you have operand 2. That is the operands that the inputs operation. Result operands are the reference of the results. And your instruction also need to specify what is the next instruction to be executed. Now, when we talk about the next instruction to be executed, at default, you have a program counter that counts +1, +1, +1. Usually, the next instruction to be executed is the next instruction in row. Unless we have a jump, we have a branch, we have a call. Where I will go back over here, and these are, we have a program control instruction. If we have a program control instruction, then I need to specify which instruction to be executed. If I have a normal instruction, then it is the next instruction. Usually it is the next instruction without any problems. Now, elements of a machine instruction. The next instruction reference. This tells the CPU where to fetch the next instruction after the execution of this instruction. So usually we need to have a hint, where do I get my next instruction from? And to do so, you have your opcode and your operand address. So if I have move 4, the CPU knows that the next instruction to be executed is the next instruction. The next instruction to be executed is the next instruction in line. The instructions are inside the instruction memory one after another. So if it's a normal instruction, if I'm in instruction number 3, the next instruction will be instruction 4, then 5, then 6, then 7, then 8, then 9, then 10, and so on. As long as I don't have any program control instructions. The program control instructions are basically the loop and the jump instructions. The loop and jump instructions and the return instruction and the call instruction. Now the number of operand addresses. Most instructions have 1, 2, or 3 operands. Now, in our studies, we are going to face basically the first two types, which is 1 operand and 2 operands. When we have 1 operand, the second operand is implicitly known. Implicitly يعني ضمنيا. You don't have to specify it. So most instructions have 1, 2, or 3 operand addresses, with the address of the next instruction being implicit. Implicit يعني ضمني. يعني I don't have to say, if I'm doing move AX BX, I do not have to say that the next instruction is the instruction after it. It is implicitly known that since this is not a program control instruction, I will go to the next instruction and then go to the next instruction and go to the next instruction and so on. Now, the trade-off of fewer addresses in the instruction result in more primitive instructions, less CPU complexity, instructions with shorter length, more total instructions in a program, longer or more complex program, longer or execution. Basically, يعني this is if you recall, we talked about 2 different types of instruction sets. There is the reduced instruction set computer and the complex instruction set computer. This we talked about inside the microcontrollers. When you are dealing with simple instructions and an architecture of a computer which is simple or reduced, you will have more primitive instructions. Primitive يعني بدائي. إيش يعني بدائي؟ يعني my instructions are simple. I have simple instructions. يعني I have add, subtract, and, or I don't have complex instructions. So I will have more primitive instructions, less complex instructions, instructions that are shorter length, with shorter length, more total instructions in a program. طبعا when you don't have complex instructions, you will end up with programs which are very long. لأنه if for example once more we do the A plus B is equal to C, if I want to do it in assembly, which is a very primitive language, then I will say move A to AX, add B to AX, move AX to C. This is 3 instructions to do a simple instruction which we write it in any programming language very easily. So you can see that when you have simple instructions, then you don't have the luxury of working with complex operations. You need to specify everything in full details. You will have more instructions in your program, longer and more complex programs, longer execution times as it is. Now we have instructions such as having 3 operands. These instructions, both the operands and the destination are for the result are explicitly يعني مش ضمنيا يعني مكتوبين بشكل واضح. When I say add x y z معناها this is add y plus z and put the result into x. So my source and the destination are explicit, واضحين مكتوبين، ما في إشي ضمني. You don't have to guess anything. Everything is written for you. So for example, if I say y plus z is equal to x, in the symbolic notation we write add x, y, z. Add the contents of memory location z to the contents of memory location y and store the result in memory location x. طبعا this is a complex instruction. We cannot do this in assembly. ما حدا يجي يحكي لي في the end of the semester, don't come and tell me that oh you wrote x, y, z. This we cannot do in assembly. This is accessing 3 memory locations in one instructions, which is not allowed. You can access 1 memory location per instruction. You can access 1 memory location per instruction. This gives a high degree of flexibility to the compiler, since it uses the cache and uses the cache memory's high speed, thus avoiding the keep of items in the register set. Uses memory as one large set. This format is rarely used due to the length of the addresses themselves and the resulting length of the instruction word. يعني لو كان هذا الادرس 16 bit وهذا 16 bit وهذا 16 bit and you have another 10 bits over here, you will end up with an instruction of 58 bits, which is too long. Frankly, this is too long. Usually we stick to our 16 or 32 bits format. So the 3 address instructions are rarely used. مش معناته we are not using them. They are rarely used. نادرا ما نستخدمهم. Okay, they are rarely used. Then we have the 2 address instruction, which is commonly used in assembly. The 2 address instruction, one of the addresses is used to specify both the operand and the result. لما أنا بحكي move AX BX معناته take the contents of register BX, copy it into AX. So this is my source and this is my destination. Okay, if I say add AX BX means add the contents of AX plus the contents of BX and store the result into AX. So AX over here is used as an operand and as a destination. طبعا operand, when we say operand يعني معامل. لما احنا نحكي معاملات الجمع هم values that are going inside the operation. Okay, so here AX is used as both an operand and a destination to store the result. So the symbolic notation for the assembly language is add x comma y, let's say here. So add the contents of memory location x to the contents of memory location y and store the result in memory location x. After executing this instruction, the contents of memory location AX will be changed. This is what I have done here. Let me do a simple one. AX is 22, BX is 11. Add AX, BX. You can see here. Now we can concentrate on this window that I'm moving. You can see here that the yellow is pointing to the next instruction to be executed. Nothing is executed. You can see here AX, BX, CX, everything is zeros. The code segment is at 700. The instruction pointer is pointing at 100 because I said origin 100 over here. Then I will do a single step. So I executed the first instruction. Now I executed the first instruction. Now AX has 22. Again, you can double click over here. You will see that AX in hexadecimal, in binary, in octal, and in decimal signed and unsigned values. All of these over here, you can see them as a byte and you can see them as a word. Then I execute the next instruction where I move the value of 11 into BX. Now BX has 11. You can see the program instruction pointer is already pointing to the next instruction to be executed over here. And finally I will add AX, BX and store the result into AX. Now after executing this instruction, you can see that my AX is 33, it has changed. BX did not change. So I added 11 plus 22, the result was stored into AX. Okay, added 11 plus 22, the result was stored into BX. طبعا just a reminder, if you don't put hexadecimal, things will become different because after that add AX 22 single step. Instead of 22 you have 16. ليش؟ لأنه 22 decimal will be 16 hexa وال 11 decimal will be B hexa. So you will add B and you get your result as 21, okay, which is 16 plus B or 16 plus 11, which you are going to get 21 as your result. So you need to be careful where, how to write your instructions. The next part is talking about the instructions. We have, by the way, instructions with one address such as mul, VL and div, let's say CX. These instructions I will come and talk about them when we reach arithmetic and logic. These are the only instructions that we are going to deal with let's say one operand, but implicitly we know the other operand. Okay, no, you cannot just multiply BL by itself. You need to multiply BL by another value. Then we have the stack memory. The stack is basically is a part of the memory. As you remember, we had different segments, and I can show you here over here. Here is the stack pointer. It's pointing to the top of stack, the stack segment, the stack pointer, and here is the stack itself. Can show you, here is my stack. It is pointing at FFE, okay, and it is moved. The stack as a stack is a little bit, it's a memory, but a little bit different. When we say stack is basically, let me show you something. Okay, so hopefully you can see this. This is a stack. This is a stack of books. Okay, this is a stack of books. Now assume that I have an empty space and I put the first book in. Okay, then the second book in, third book in, fourth book, I can show you like this, fourth book in, then fifth book, then book number 6. The stack works in such a way, last in, first out. So this book will go out first, then this book will go out, 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 and finally this book will go out. This is called last in, first out. This is called last in, first out. So a stack is a data structure memory in which items are stored or pushed into one order such that A, B, C are then retrieved as C, B, A. This is called last in, first out. Last in, first out. Or push down list. Last in, first out. Whoever comes in last goes out first. A stack is an ordered set of elements, only one of which can be addressed at a time. The point of access is called the top of stack. We cannot access the stack from any other place rather than the top of the stack. The point of access is called top of stack. The number of elements in the stack or length of the stack is variable. Items may be added or deleted from top of the stack. How to deal with the stack? I'm going to show you a little bit faster over here. Let me close this. And stack operates this way. I will say push AL, pop BL. Stack operates with two instructions which are push and pull. طبعا push AX, it should be AX, pop BX. Okay. Stack operates with push and pop. Push means putting in the data, pop means taking out the data. So I can show you here the stack on the side. So we did the addition and we can show here. So if I can show the instruction. We are here going to do the addition. Then I'm going to push. Okay, I'm going to push AX. What is the contents of AX? It is 0021. So 0021 is stored in the first location. Then pop BX. Now the stack will go back to the top and BX will have the value of the stack. So we are going to talk about them later on in module 4, but this is one type of memory. Remember, the memory itself, we said it's divided into 4 different segments, which were the code segment, the data segment, the stack segment, and the extra segment. So the stack is part of the memory, but it is accessed using push and pop. طيب, why we don't use it and give it values and like the data segment? Basically, this is faster. Instead of giving addresses and these things, no need to think, just push and pop the information very fast. Now push, amend a new element in the top of stack, pop, delete the top element of the stack. So it's an array operation where perform the operation on top element of the stack, replace the top element with the result, and then we have the binary operations which is performed on top of the stack, delete the top 2 elements of the results and place the results of the operation on top of the stack. This is basically talking about the stack memory. So I will stop over here and we will continue inshallah at 1 p.m. If you have any questions, I'm happy to answer them.